All right, hello everybody. My name's Connor Smith. This is Eric Dundas. We are SOC Liu with a 3D map of UNL's city campus.
Our sponsor is the UNL School of Computing, specifically Dr. Liu, one of the professors here. The School of Computing has an ongoing project with a goal of scanning city campus and creating a map that can be used for autonomous vehicles. All of the research that we contributed to was for autonomous vehicles and autonomous driving. Our team was tasked specifically with taking the scanned data from these manned vehicles and turning it into a map for autonomous vehicles to reference. And additionally, our team was also tasked for creating a harness for LiDAR scanning that could be worn in a backpack for any person to be able to collect data by themselves.
So, meeting the sponsors. First, we have our chief sponsor, Dr. Qiang Liu, an associate professor here at University of Nebraska-Lincoln. We have the product owner, Dr. Chun-Sing Ho. He is a professor at UNL, he owns one of the autonomous vehicles. Graduate research assistant Yung Jae. He was our primary sponsor contact during the first semester, and then graduate research assistant Jae, who has been our primary contact this semester.
And our faculty team, the faculty members here at UNL that were working with us on our end development side. First, we have the project manager, Bill Browning. He was a big help. All of them were a big help. We also have the tribe lead, Dr. Shruti Bullman, as well as our coach, Stephen Slater.
And then our team. We were an interdisciplinary project, so we have a couple of mechanical engineers on the team. First one, Mike Morris, all the way on the left, is one of our mechanical engineers. We have Eric, who you've already met. He is the development manager and also the team lead of our team. We have Colton Hill, Colton Johnson, both of them are developers. We have myself, I was the product manager and also a developer. We had Jacob Klaus, also a developer, and then we had Jacob Cody, our other mechanical engineer.
We were tasked by Dr. Liu and his graduate research team to help with automated vehicle research, predominantly with data collection and assembly. So that meant using LiDAR to scan in 3 dimensions. Basically, the LiDAR sensor uses lasers to scan finding points on objects and using the distance and time between receiving that point back to create images or create frames in 3-dimensional space. We were also focusing on parsing this 3D data and turning it into a map that could be used. We also would add a layer of annotations and basically to have the map turned into roads that the robot could then, or robot and van, all of these automated vehicles to read and use to drive autonomously. With that setup, they could be used for further research. Additionally, we were asked to create another method for data collection. Part of the graduate research team was tasked us with creating a harness that could hold a LiDAR sensor, and that sensor could help with 3D scanning by a singular person rather than a vehicle or a robot.
So for our product solution, it was a lot of methodology. This is kind of an overview of how our project operated. We would start with some kind of scanning method, either with a full-size autonomous vehicle or a small robot that used a LiDAR sensor and operated in ROS, which is the robot operating system. That would then be fed into a SLAM algorithm, which stands for simultaneous localization and mapping, which basically would take out all the 3D data and put it into a single file, a single 3D file. We had several of these sometimes, which would then be fed into Blender, in which case where we would assemble them all and then export that to be a single larger map. And then this was fed into Vector Map Builder, which we used to add that layer of annotations that could be understood by an autonomous vehicle, which would then end up with a completed HD and 3D map. And as we go through the next slides, you'll kind of see a little bit more detail about each of these steps. So the first step is the data collection. Here we have both of the methods we used in first semester. We largely used the full-size vehicle, that van, which has a LiDAR sensor mounted to the top of it, as well as this smaller robot, which is on display at our booth, and what we primarily used during second semester. Both of these operated with Robot Operating System, or ROS, which was a system that we needed to learn to interact with in order to get data off of these machines.
Next, we are able to see what the ROS kind of shows to the user, or even when it's being manned indirectly. Basically, this is RViz, which is an aspect of ROS. And so part of what RViz does is let us see the types of data that is being recorded by the robot, as well as while running bag files for the SLAM algorithm, it allows us to see the current frames that it is playing in the ROSBag playback, as well as partial constructions of the final PCD file. And then here we have what PCD actually looks like. This is output from the SLAM algorithm that we used, and that is what isolates all of the 3D data from the rest of the data that the robot would actually collect. There's a lot of detail in it. You might be able to recognize this is Memorial Stadium along in the back here. Over on the edge there is Avery Hall. I believe this is Old Father, and I forget what the other halls around it are named, but this is part of campus. Even though this is a very clear representation of parts of campus, some parts of campus, especially when you look closer, do not look as detailed as you might need. And so with the help of some students at the Carson School for the Arts, Carson Center for the Arts, we were able to create this mesh visualization in Blender of the data that we collected. This is only a partial data reconstruction. Some of our later scans are not a part of this, this image itself, but this was helpful in joining some of these data scans together, because the point cloud data does not give a good enough detail at close range of what specifically is a wall, or what could be used to join these scans together. Additionally, some more notable landmarks around campus show up a lot better with the mesh visualization. So Archie, normally in Blender, you can tell that this might be Archie the woolly mammoth right outside of Morrill Hall, but using the mesh visualization, you can take a better look at our good woolly mammoth that we have here on campus. And then finally, we have the LiDAR harness itself, the thing that our MME students, our mechanical engineers, worked on. Like I said, this is an interdisciplinary project, and so our mechanical engineers were tasked with building a LiDAR harness. The design was inspired by some existing designs that the sponsor had given our mechanical engineers to kind of go off of. SolidWorks was mostly used for the design work. The College of Engineering machine shop was used to kind of put it all together, and then this, in combination with a backpack, a power source, and a laptop, would allow for some more mobile data collection methods. Overall, what we presented to the graduate research team, as well as Dr. Liu, would be a 3D map of Innovation Campus and City Campus, methodology for data collection, computation, combination, and visualization, as well as a prototype of an additional method for data collection and research. Some of the highlights of this project were we got to experience ROS, which is something that up until this project I had no idea existed. Same with Vector Map Builder, what we used to build that layer of annotations, along with Blender.
and learning how to interact with LiDAR and IMU sensors. We also hope that this helped accelerate the research for automated vehicles by providing a 3D map.
Thank you very much. And Jahe, we'd like to present this award to you.